This is Chapter 8 on what are called sampling distributions. This will be very familiar from Chapter 7. Everything we learned about in Chapter 7 will still remain true for Chapters 8, 9, and 10. And this is just kind of taking Chapter 7 one step further. This time, instead of looking at a population, we're going to be looking at samples. And so we're going to talk about sampling distributions for means, which is what we've been discussing throughout the whole course. And then something new, sampling distributions for proportions. Now that's a new concept, and we'll kind of learn some new things about proportions, which are different from means. And this difference, means and proportions, will continue throughout this chapter, Chapter 9 and Chapter 10. So we'll kind of distinguish between the two. I'll show you the similarities and the differences. So we're going to kind of discuss the concept of sampling versus populations. So if I made a list of all the student averages over all the semesters I've been here with Lone Star, I would have well over 1,000 different data points. So I had a big long list, maybe in Microsoft Excel, of all the semester averages I've ever had from all the different students I've had over all the semesters. So that would be my population. I have over 1,000 data points in my population. What I can do then is take samples of a chosen size, let's say size 10, and I can take samples of size 10 from my population and compute their means and standard deviations. This creates what's called a sampling distribution. So instead of having the entire population, I have a bunch of samples of size 10. So I take 10 student averages, that's a group. I take 10 more, that's the second sample. I take 10 more, there's another sample, 10 more, and I can repeat this process over and over and over again and have a whole lot of samples of size 10 with a whole lot of averages and a whole lot of standard deviations for these samples. And I create what's called a sampling distribution. Each sample mean of each size 10 would be slightly different from the population mean, from the true mean. It would be a little different, but relatively close to the true average. Each sample standard deviation would be slightly smaller than the population standard deviation, and that's because the samples have less variation than the population. We're only taking size 10, samples of size 10, so we don't have as much room for variation. Whereas if I have over 1,000 data points, there's going to be a lot of variation all over the place. So the sample means will deviate a little bit from the true mean, but it'll all focus around what we call the true mean or the population mean. And the standard deviations would be slightly less. They'd have a little bit less variation than the population. And that's what happens when you take samples. So lots and lots of samples of a particular size coming from a population. So there are some conclusions we can come to about sampling distributions. The shape of a sampling distribution is approximately normal or bell-shaped. We talked about normal in Chapter 7. Normal or bell-shaped, given that the population is normal. So if I look at the histogram of the entire population and it's bell-shaped, then when I take samples, they're also going to be bell-shaped. The center of a sample distribution is the average of all those sample means. So if I averaged up all those sample means, it would be equal to the population mean. So each individual sample mean will be a little different, but if I take all of the samples and average those all together, I would be exactly equal to the population mean. And the spread of the sample distribution, which would be the sample standard deviation, would be slightly smaller than the population. So slightly smaller than the population standard deviation. I think I'm missing a word there. Slightly smaller than the population standard deviation. So this is kind of the shape, the center, and the spread that describing the distribution for samples versus populations. I have it summarized again on the next page. So the notation we use for the average of all the means of all the possible samples of a particular size is labeled mu with a subscript x bar. That is the mean of all the samples. So the average of the averages is equal to the true mean of the population. So this is what we call the true mean, and this is the mean of all the samples of a particular size. In our example, I use size 10. The standard deviation of all possible samples of that particular size from the population is labeled sigma of x bar. So it's all the possible samples. If you take the standard deviation of all of them, it will equal, this is a slight adjustment, the true standard deviation over the square root of the sample size. So this sigma is the true standard deviation, and this is the square root of the sample size. And both of these are clearly labeled in your formula sheets. On the second page of your formula sheet, if you go down to chapter 8, you'll see that the mean is equal to the true mean, and the standard deviation gets adjusted in that particular way. And then we'll get to those second two bullets in section 8.2. So you don't have to memorize this. It is stated on your formula sheet and discussed on page 370 of your textbook. So you're going to hear a new word moving forward in chapters 8, 9, and 10. The standard deviation for a sampling distribution is also called the standard error of the mean. So you might have heard a phrase margin of error, or give or take a certain amount of error. So if you hear standard error of the mean, that is the same thing as the standard deviation of the sample. So a new word calling it standard error instead of standard deviation. So that's just a new expression. All right, so let's look at a quick example here. If the average IQ score is 100 with a standard deviation of 15, we're using the same example from back in chapter 7. If we took a sample of size 9, what would be the mean and the standard deviation? We know that the mean of all the possible samples would be equal to the true mean of the population. And the standard deviation of all the possible samples would be the true standard deviation over the square root of the sample size. Well, the true standard deviation is 15, the square root of 9, and you can work that out in the calculator, or we know that the square root of 9 is 3, and 15 divided by 3 is 5. So the standard deviation for the samples would be 5. So again, it gets smaller because we're taking a sample instead of looking at the entire population, so the variation gets smaller. Same idea, if we took a sample of size 25, what would be the mean and standard deviation? Well, the average of all those samples would still be 100, and the standard deviation this time would be 15, the true standard deviation, over the square root of the sample size, which is 25. And the square root of 25 is 5. I chose these particular numbers, or the book chose these particular numbers on purpose, so that you can get a nice answer. In reality, these numbers will not always be perfect squares. But just for the purpose of having a nice clean example, these work out to nice integers. So the mean stays the same. Whatever is given in the problem, it will stay that way for the samples. And the standard deviation has that slight adjustment. That is kind of the big idea of sampling distributions. I mentioned previously, if the population distribution is approximately normal or bell-shaped, then the sampling distribution will also be approximately normal or bell-shaped. So if I look at the histogram of the population and I see that it's bell-shaped, I can know that when I take a lot of samples of a particular size, when I plot all of those, it will also be normal or bell-shaped. Then the question becomes, what happens if the population is not bell-shaped or not normal? So this is example 4 on page 371. This histogram represents the number of people living in a household in the United States. It is known to have a mean of 2.9 and a standard deviation of 1.48. So if we look at this histogram, hopefully you can immediately recognize that the majority of the data are on the left and it trails off to the right. So this is a skewed right distribution. It still centers around 2.9, which is somewhere in here. There's your mean. and your standard deviation is about 1.5. And so it's a little off. We can't just kind of evenly space it out because we've got these high outliers here skewing our data to the right. So are these data approximately normal? No, they are not. So this is the population of the average number of people living in a household in the United States. Most of us have between 1 and 4 people living in our house, and then you have these extremes up to 5, 6, 7, 8, maybe even 9 or 10 people living in the house. So these are extreme cases, and it skews the data to the right. So this population is not normally distributed. But a computer software program obtained 1,000 samples of size 4. So from that population, it pulled out samples of size 4, and it repeated this process 1,000 times and calculated the frequency of each of these values and created this histogram. Notice, I know these numbers are a little blurry. This is 2.8, and this is 3.2, 3.6, 4.0, and 4.4. So it got a little bit more particular with the values, 2.0, 1.6. It kind of zoomed in here. But I want you to notice right away how nice and symmetrical this distribution is. If they kind of did that for you. They kind of ran a bell curve right over that histogram. Notice that it's centered around 2.9, somewhere in there. That's about 2.9. And our standard deviation is going to get a little bit smaller. 1, 2, 3, 1, 2, 3. But our distribution became normal. The sampling distribution became normal. Even though our population was skewed, if we take 1,000 samples, it becomes normally distributed, centered around the mean, and with the standard deviation a little bit smaller than the population. So that's what happens even if our population is off, even if it's skewed. If we take enough samples, if we take 1,000 samples, then our nice histogram becomes normally distributed. So this concept is called the central limit theorem. And it says regardless of the shape of the population, the sampling distribution becomes approximately normal as the sample size increases. So as we get bigger and bigger and bigger, our histogram starts to become normally distributed. So in order to safely assume that the sample distribution will be approximately normal, they decided that a sample size of at least 30 is appropriate. So if the sample size is greater than or equal to 30, we can safely assume that the sample will be normally distributed. Now they came about 30 using some calculus, which we don't need to worry about. We just need to remember that magic number 30. If the sample size is at least 30, we can safely assume that the sampling distribution will be approximately normally distributed. If it's less than 30, we learned some techniques in 7.3 of how to check to see if the data are normally distributed. Sometimes it will just state it in the problem just to assume that it's normally distributed, and we won't have to do this check. But in the real world, we always have to make sure our sample size is big enough so that we can safely assume that it's normally distributed. So that's called the central limit theorem. So I just have a few examples. You might want to get out some notebook paper for these. There's not much room on the slides because I wanted to make sure the font was big enough for you to be able to read it. It gets a little crammed sometimes. So here's an example about gas mileage. It says, based on tests of a Chevy Cobalt, engineers have found that the miles per gallon on a highway are normally distributed. So those are the key words we need. The mean is 32 miles per gallon with a standard deviation of 3.5 miles per gallon. Now again, before we even read the first question, because we see the words normally distributed, I always suggest drawing a nice bell curve. This is for problem 24. On page 377. I just pulled some of these out of the textbook exercises. So it's centered at 32, and we can count 3 to the right and 3 to the left. So 32, and we'll add 3.5, add 3.5 again, and one more time. Take 32, we can subtract 3.5. Subtract it again. And one more time. It just kind of gives us an idea of where our data fall. Now we can read the first question. It says, what is the probability that a randomly selected cobalt gets more than 34 miles per gallon? So this question sounds exactly like the questions in Chapter 7. We're just worried about one car, a randomly selected cobalt. So for part A, we're going to do a normal CDF. We want more than 34, which is somewhere here, and greater than 34. So that's the portion of the curve we're looking at. That means our lower bound is 34. Our upper bound is positive infinity. Remember, that goes to infinity. Our mean is 32. And our standard deviation, because it's just one car, is just 3.5. And we can run that, normal CDF, just like we did in Chapter 7. And we get 0.2839. And you can round that however is appropriate, but that's about 28% chance that a randomly selected cobalt gets at least 34 miles per gallon. Now question B is a little different. Question B says 10 cobalts are randomly selected and the miles per gallon are recorded. What is the probability that all 10 of them, the average of all 10, exceeds 34 miles per gallon? Now, we're kind of looking at the same curve. However, when we want 10 cobalts to fall in this range, our standard deviation gets smaller. So I'm going to go ahead and redraw this with the new standard deviation. Remember, we take the original and divide by the square root of the sample size. So we're going to take that original 3.5 and divide by the square root of 10. And I'll round that off. 3.5 divided by the square root of 10 gets me down to 1.1. So our standard deviation, or our spread, just went from 3.5 down to 1.1. So if I redraw this curve, it just got taller and skinnier. Still centered at 32, but this time the standard deviations are much narrower, and we only add 1.1. Add 1.1. And one more time. Whoops, 0.3. And then subtract. You don't always have to redraw this curve. I just want to show you what's happening when we made our standard deviation so much smaller. The original curve spanned from 21.5 to 42.5. Very low and wide spread. Well, now we've just shrunk it by almost 3 times smaller. So the center is still at 32, but notice that the highest value is going to be around 35 and the lowest is going to be around 30 or 31. So we just shrunk that span. And that's because if I want all 10 cars to average out to a value, my range is going to become much smaller. So even though our target value is still 34, 34 now falls much further up on the curve. So I have a lot less space that I'm shading because it's much less spread out. So I'm still going to run a normal CDF. My lower bound is still going to be 34. My upper bound is still infinity. My mean stays the same. But this time my 3.5 just became 1.1. Now in the calculator I would put this calculation. I would not round. So 3.5 over radical 10. I would not use the rounded value, but that is approximately 1.1. And let's see what that gives us. Instead of 28%, we should be getting a much smaller number. So if you can hit second enter if you want to. Let's see. Pull up your normal CDF again. So you can pull it up by pushing second enter. Everything stays the same except for the 3.5 now gets divided by, whoops, the square root of 10. And use a double parentheses to close it. So it's still 34 to infinity. Our mean is still 32, but now we take the 3.5 and divide by the square root of 10. And look what happened to my 28%. I just got 0.0354, only a 3.5% chance now. So it went from 28% to 3.5%. Much, much smaller chance that all 10 cars are going to get such good gas mileage. And let's look at problem C. Now we're looking at 20 cobalts. 20 cobalts are randomly selected, and the miles per gallon for each car are recorded. What is the probability that the mean miles per gallon exceeds 34 for all 20 of them? So this is going to be even more extreme. So this time we take our sigma and divide by radical n. We take that 3.5 and divide by the square root of 20. This is going to make a very small standard deviation. Very tiny, 0.783. And I'm not going to redraw the curve, but we can visually see that it just went from 3.5 down to 1.1. Now it's down to less than 1 mile per gallon spread. So my curve just shrunk even more. So that tail that I'm shading is now even smaller. So when I do a normal CDF, same setup, 34 to infinity. The mean is still 32, but my 3.5 is now getting divided by the square root of 20. So again, you can hit second enter and change the 10 to a 20. And look how tiny that number just got. Very small. 0.0053. So it went from a 3.5% chance down to a less than 1% chance. So part C asks, is this result unusual? Yes. Very unusual. And if you think about it, if I have a sample of 20 cars and I'm recording their mean miles per gallon, the chance that that average is going to be over 34 when the true mean is 32 is very, very rare. It's going to get closer and closer to that true average the bigger sample I take. So hopefully this logically kind of fits in. And if I just need one car, the chances are pretty good. 10 cars having an average over 34 is a little rare. 20 cars having an average over 34 is almost not going to happen. Alright, so that's what happens when you sample. The chances of these extreme values get smaller and smaller, and it gets closer and closer in to the true average. The bigger sample you take, the closer it becomes to the true average. So that's what happens with the sampling distribution. Alright, I have a few more examples here. I'm not going to draw the curve anymore. I think we're getting used to how this works. So this is from problem 16 in the textbook. A simple random sample of size 36 is obtained from a population with a mean of 64 and a standard deviation of 18. Part A asks you to describe the sampling distribution of X bar. So part A is asking for three things. When it says to describe, it wants the shape, it wants the center, and it wants the spread. So those three characteristics describe the distribution. Now the shape we're hoping is normal. We can say it's normal because 36 is greater than or equal to 30. So because our sample size is at least 30, we can say that it's normally distributed. Our center is going to equal the true mean, 64. And our standard deviation is going to be 18 divided by the square root of 36, which 36 is a perfect square, and that should give us 3. So our standard deviation went from 18 down to 3 when we take a sample of size 36. So part B, we're going to use these values. What is the probability that our sample will be less than 62.6? So for part B, we're going to do a normal CDF because we're allowed to say that it's normal since our sample size is big enough. Less than 62.6 would go from negative infinity to 62.6. My mean is still 64, and I'm going to use my adjusted standard deviation of 3. So second bars, normal CDF, negative 10 to the 99th power. 62.6 is my upper limit, mean of 64. And our standard deviation has already been adjusted, and it worked out to an integer, so I can just use that integer of 3. And there's my result, 0.3204. So be careful with your rounding. I always use 4 digits. If you're going to round to 4 digits, you're going to take that the 5th digit and round off. So the 6 rounds the 3 to a 4. So again, if you have trouble rounding, the homework's going to be frustrating as well as the test because you have to be very careful with your rounding. Part C, what is the probability that the average is greater than or equal to 68.7? So this time I'm going to do normal CDF. Greater than or equal to 68.7 is from 68.7 to infinity. If you need to draw and shade, that's fine. There's nothing wrong with drawing and shading. I'm just skipping that step. Average of 64, standard deviation of 3. So second bar's normal CDF. 68.7 to infinity. Whoops. Same mean, same standard deviation. 0.0586. And part D, what is the probability that it's between 59.8 and 65.9? These are usually the easier ones because it gives you your lower bound and your upper bound. So 59.8 to 65.9, same mean, same standard deviation. Now because we're in the middle here and hovering around the average, this probability is going to be larger because our standard deviation squishes everything to the middle. So normal CDF, 59.8 to 65.9. Average of 64, standard deviation of 3 gives us a large percentage, 0.65. That would round to 0.6560. So if you're looking between two values in the middle, it's going to be a larger answer because that's where the majority of your data fall. If you're looking for extreme lows or extreme highs, they're going to be smaller because the standard deviations for the samples get smaller and smaller, which makes the tails smaller and smaller. So it's just kind of a generic question. It doesn't have a scenario attached to it. It's just kind of running through the motions. And always feel free to draw the curve. So if drawing the curve helps you visualize what you're looking at, we would put our mean of 64. And we would use our adjusted standard deviation of 3. And that might help you draw and shade. Remember, positive infinity to the right, negative infinity to the left. I'm going to pause there, and then I'll do the last couple examples.